Earth, gravitational field, our building, and the usual assumption that we have this homogeneous, this uniform field in a uniform gravitational field like in this room, at least according to the usual approximation. Now, what is a uniform acceleration? We can describe it as an acceleration of 9.8 meters per second squared throughout this building. I let go something over here, it falls down to the ground. I'm going to describe it as accelerating. We can model what's happening with there is an equivalent accelerative push up that's exactly equal for all of them. And as we mentioned, that is completely indistinguishable from some kind of an interplanetary building, rocket, which is all the way maybe in intergalactic space, totally empty of matter. There's no gravitational field that's measurable, and there's nothing even visible, maybe no galaxies visible anywhere nearby. And everybody in that building is feeling that acceleration. And since it's just an acceleration, then obviously it doesn't matter if you're on the third story or the second story, the first story, or what side of the building you're on, you're all feeling, you all have exactly the same acceleration, and therefore you're going to feel exactly the same accelerative push, so to speak, on your feet, irrespective of your mass. Obviously it doesn't depend on your mass, it depends on the acceleration that this rocket ship building has. So there it's no surprise. What's surprising is that in gravity, it happens that way, that everybody here feels the same accelerative push. And that's why we can model what's happening here in this building on the planet Earth with an intergalactic traveling spaceship building. And any measurement that we make will be the same in both. They're indistinguishable. A particle falling, we have ourselves, we describe it one way, the particle described, the frame of the particle describes itself in a different way, but it'll see us as accelerating, which is fine because we feel these accelerated forces. So we're not inertial. We're not surprised to find that this inertial particle considers us to be accelerated. The description is not going to change the actuality of what's happening. It's a perspective. And one should always be able to change from one perspective to the other if one understands the physics. So in a uniform field, there'll be two phenomena. Any inertial particle that you let go from outside will seem accelerated by those in the plate, which models exactly what happens if you're standing in the building and let something go. It looks to you as accelerated. Those who consider it accelerated will feel this accelerated push on themselves, we call the normal force to our weight. We'll also feel an accelerated push on their feet over here that obviously will be due to the acceleration. Now, the strong equivalence principle claims that any physics experiment that one would make in empty intergalactic space in this interplanetary rocket building would give exactly the identical results. An electromagnetism experiment, light experiment, anything will give exactly the same results as here on planet Earth. In other words, if you want to know how does gravity interact with some other force phenomena, and you wanted to do an experiment here in the lab, and you were wondering how to do the equations, you could, if you want, just go into intergalactic space and do the experiment there in a rocket. Now, of course, you say, well, it's kind of difficult, I don't have the budget for that. So what do? So we can do just ignore gravity, pretend there's no gravity, and just write the equations for an accelerated platform or rocket or building, whatever it is, and put in your phenomenon there and just see how it would work in an accelerated frame. So you're going to have regions. This is our building over here. This is a building in some other country on the planet. This is a building on the other side of the planet. Everywhere there's going to be some region where in that region it's going to be a uniform gravitational field, just that it'll be pointing in a different direction than our uniform gravitational field. And if you have a really tall building, then maybe we'll have to divide it into 2 or 3 different uniform regions. And if it's a very strong field in some planet that's very, very dense, maybe every floor has to have its own little G. But you can always find some small region where, to the extent that you're able to measure, you have pretty much a uniform field. And in an arbitrary gravitational field, where you can have all kinds of different field directions and strengths, you can always find some small region. Of course, they're not building the regions of space. And so we'll model any gravitational field by a collection, a very large collection, maybe even an infinite collection of tiny or infinitesimal regions in each of which we can consider the field to be uniform. Now, again, remember, that's any gravitational field. All right? It's this collection of uniform fields. So since we can model any one with a rocket, we can model this collection with a collection of rockets. So this is a gravitational field, arbitrary. Each region has its own uniform field. In each region, we can model it by an acceleration. We'll produce an acceleration in this region would produce exactly the same phenomena as would be measured in the gravitational field. And so we can then model all of these. We can model each of those with an acceleration. So you'll have a whole bunch of different regions. Each one has its own acceleration. So whatever would happen in this gravitational field will happen in intergalactic empty space, where we create a region far from any gravity. This is gravity. We take a region far from any gravity, far from this field, and we simulate it. We model it by putting in these plates or buildings, accelerated rockets. This situation of this collection of rocket plates is completely physically indistinguishable from the situation of gravity, let's say, of the planet Earth, all these buildings, and the free fall particles, and so on. We have this very interesting idea that we could model an arbitrary gravitational field by a collection of regions, each of which has a uniform acceleration.